So this brings us to a slightly more interesting problem called the top k problem. So here's the idea. Imagine we've got our list of values L, and there's n values in the list. We can compute the max or the second max, second largest, just like we've been doing, but in some sense it doesn't really give you a very representative sample of what the list is about. Sometimes it's nice to have a bit more. So let's imagine that this list is sorted, though it turns out it won't have to actually be sorted. And imagine that we're going to focus in on just the ones that would be at the best, the k best out of the n. It could be the k smallest or the k largest, depending on the particular application that you're considering. But knowing, a bunch of the ones near the top instead of just the very tippy top can be very instructive. So one natural strategy is to iterate the max procedure. So go through the list, find the max, pull it out of the list, so the list is now n-1 long, and then repeat this. Each time we compute the max, it'll be actually the second, the third, the fourth largest from the original list, but it's always the max of the current list. This is a pretty reasonable thing to do, especially if k is small. You just need 1 or 2 or 3 of the top values. So another natural thing to do is just sort the whole list. Once we've sorted the whole list, the first k elements of that sorted list are exactly the ones that we want. So this is actually a very simple way of doing it. In Python, it could just be essentially 1 or 2 statements. Insertion is another strategy. This is the generalization of the solution that I gave for the find the second best example before. In that example, I kept track of both the best and the second best, and then was running through the list, and each new element of the list that was encountered, figure out where it would fit into that top 2 list. If it was smaller than both of those, ignore it. If it's bigger than both of those, put it at the top of the list and bump the list down, and so forth. So as always, we're trying to find the best algorithm that we can use to run on our data. So which of these algorithms has the best big theta? And I'm going to give you a hint. We're looking for the top k out of a list of n elements, but k, we're going to look at this question for different values of k. In particular, if k is half of the list, we want the largest half of the list. The question is, are we better off using selection or insertion? Both of these are going to have the same big theta for all these examples, so I just grouped them together. Or is it better to sort the whole list, keeping in mind that sorting is a big theta of n log n operation? Say you want to find the best root n items. Is it better to use selection or sorting? If you want the top log n items, which one is better? This function is the logarithm of the logarithm of n. So as slow growing as logarithm turns out to be, this is even slower or growing, the logarithm of the logarithm of n. So which one would you choose in that case? And finally, let's say you want the top 100. This is a common thing that you see on the internet a lot. Top 100 movies, the top 100 Beatles songs, the top 100 times I've used the phrase top 100. There's lots of different contexts in which this appears. And if you're going to do that, are you better off using a selection or insertion algorithm or to sort the whole list? So what I'd like you to do is, for each of these columns, check this box or that box, or if they are big theta of each other. In other words, from an asymptotic standpoint, this algorithm and this algorithm will run the same, worst case, asymptotically, then check both of the boxes.